Okay, so when I came and was talking to you guys last year about, how do they figure out who's going to be the next president? How do they get the ±3 for presidential election? Well, that's what we're going to do right now. Your knowledge of that sampling distribution, we can now create a confidence interval. Let me just make up a problem. Let's say you went and did a random sample of 1,200 people, and you found before the election, okay, from your sample, that Obama was going to get 51% of the vote. Okay, let's build the confidence interval. Let's build that confidence interval they put on television. So let's go ahead and do that. Let's go do a confidence interval for this problem. Okay, like I said before, we're doing the same stuff we did last chapter. It's just we're using proportions now instead of means. So, population proportion. What are we going to say here? What are we looking for? Ah! True proportion, right? We're not doing means anymore, right? We're not doing mu. Okay, so this time it's the true proportion of vote that Obama's going to get on election day. Okay, so I'm not going to see any more mu's, right? I'm not going to hear the word mean. We're doing proportions now. Okay? All right, assumptions. What's going to be our first assumption? It's going to be what we did before, right? Simple random sample. We want to check out to make sure we're not standing outside of Democratic headquarters taking our sample, right? We're going to get one of the extreme p hats if we do that. All right, the second assumption. That's the guy we did up there. We're trying to see if that formula works, right? So is the standard error of the proportions equal to square root p 1 minus p over n? Right? We're just checking out to make sure that formula is the right one. Same check we had before. Okay. How about assumption 3? What do we got going on here?
Is sampling distribution of p hat?
Yes, very good. Now, I still got some of you losing points on this. I had some of you write normal sampling distribution question mark. Well, if you don't want to write stuff, I can write stuff. Okay? Is the sampling distribution of p hats normal? Write it out. Okay? But here is it all p hats going to take on a normal shape. All right, what's our test over here? N times p. N times 1 minus p must both be greater than or equal to 10. Go do that assumption. What? Did you just say I don't know?
Yeah.
That's the right thing to say. Why? What don't you know?
The question.
Oh, that's not this one. I need you to not know something else. What don't you know? No, I said 1,200. I said there's 1,200 people.
Yeah. Oh, is that true?
Yeah, I don't know this, do I? In the warm-up, didn't I tell you that the true the true proportion was 47%? Do I know when he's going to get on election day? Do I know what that is right now? No, I've got a problem. What do you want to do? You want to get a different teacher because the teacher's got a problem. I get that. What do you want to do?
Use 0.5.
No. Don't be looking ahead to notes. You don't even know what you're looking at. What do you think? Any ideas? This kind of goes into last chapter. Yeah.
Take a sample.
We have. I already told you, right? Didn't we take a sample of 1,200? What did I say that the sample proportion was? What did I just tell you? I just told you what the sample proportion was. 51%, right? So what do you want to do?
Use the sample.
Use that, okay? We don't know what the population parameter is, but we have an estimate, right? We can use our p-hat. So let's just go ahead and do that. So right here, we're going to deviate from this formula a little bit because we have to. I don't know what the population parameter is, so I'm going to have to use my sample proportion. So in this problem, what we got? 1,200 times 0.51, 1,200 times 0.49. Remember, you got to go figure out those numbers. I think one's going to be a little more than 600, one's going to be a little less than 600. But they're both greater than or equal to 10, so we're okay. We'll have a normal sampling distribution. Okay, what's our test statistic? Okay, we're going to start with our point estimate. That's going to be the 51%. That's what's going on the television, right? We predict Obama's going to get 51%, plus or minus, and this is our margin of error. It's going to be Z-crit times the standard deviation of the sampling distribution. All right, let's start plugging in some numbers. I told you that the p-hat from the sample was 51, so 0.51 plus or minus. What is the Z-crit? Now notice we're not in, their t distribution doesn't exist anymore for us. Why did we use the t distribution last chapter? What was the reason? Didn't know the population standard deviation, right? There's no such thing now! Doesn't even exist in the first place! So we don't even have to worry about that anymore. So we don't use the t distribution. Okay? We're going to use the z distribution. So what is the z-crit value for, let's do a 95% confidence interval? 1.96. You guys got that memorized? Good. 1.96 times the square root of? Yes. What? That's not what the formula says.
We don't know.
We don't know that, do we? So what are we going to have to do again? Yes. Okay. Does everybody see that? The formula says we have to use the population proportion, but we're doing a confidence interval. We have no idea what that value is. So let's just use our p-hat again as an estimate. So we're breaking away from the actual formula twice in this problem because we just don't know what that value is. So I agree. We will use p-hats here. That's going to be different over here in a second. But understand, in a confidence interval, we don't know what that value is, so we're going to use an approximation. So what? 0.51, 0.49 over 1,200. Throw that guy in your calculator, see what you get. Go find that margin of error. Make sure you can do it in your calculator. What'd you get? 0.028 is correct. Did you guys learn either in government or AP government that when they do these presidential polls, they take around 1,200 or something like that to get that margin of error around 3%? That's it. All right, what changes in the conclusion? Nothing. Just don't use the word means, right? So what do we have here? Before taking our sample, 95% of the sample proportions I get would create an interval that captured the true population proportion for Obama's votes. Okay, our confidence interval is. And this is what they give you on television. We predict Obama's going to get 51% of the vote, and on the bottom they say with a margin of error of 2.8%. That's it. That's what they do. You got the skills. Had a good question, third period. I don't know if, I think I talked to this guy, Michael Silver. He's a statistician who predicted all the states correct. Just absolutely nailed everything. Now, is he using any different formulas than the other people are, Gallup and all those other poll people? What do you think he did well? No, they usually 1,200 or 2,000. They same amount of sample size. Yeah, I don't know about that, but he took good samples. Okay. Now I haven't read his work. Someone said that he thought maybe he took a bunch of other polls and kind of put those together. So that might have been how he did it too. But the key is right here, right? If I'm standing outside of Democratic headquarters, all this stuff is garbage, isn't it? Because I'm going to get a p-value, a p-hat here around 98%, right, or 100%. Okay. So that's the key. That's the key step in this. Okay. So what's different about a hypothesis test? All right, let's say, and by the way, on tonight's homework, if it ever says, is there evidence, that's your key words for a hypothesis test. Okay, so you're going to have some problems. Is there evidence to say that's hypothesis test? All right, here we go. I'm going to make up a problem. So before you start, let's say you want to make sure Obama's going to win, so you want to prove that he's going to get more than half the vote. That's your goal. That's your hypothesis test. Do we have evidence that he's going to get more than half of the vote and win the election? All right, let's talk about what changes here now. So we'd say, is there statistically significant evidence that he's going to get more than half the vote? That's how it would be asked. Anything change here? What we did before? No. Population parameter, we're still looking for the true percentage of vote that Obama's going to get on election day. All right, how would you set up your null and alternate hypothesis here now? Now remember what I said. I want to see if there's evidence that he's going to earn more than half the vote. How would you set this up? P, first of all, good, right? No more mu's. No, we're doing, want to know the proportion? P is equal to, yeah, or, well, let's use it as decimal, so 0.50, very good. You could put 50%. It means the same thing, right? Very good. And notice we didn't have any 51s in there. We're not looking at our p-hat. We're trying to prove that it's greater than 50%. What would our alternate be? Greater than 0.50? Now, this changes everything. This changes everything. Remember, in a trial, the null hypothesis is that they're innocent. So we assume they're innocent throughout the entire trial. Well, in a hypothesis test, we assume that's right. So let's see what that changes and what that deals with. All right, our alpha level. Well, let's match it up there with that guy. That was a 95% confidence interval. This is one-sided. What would this alpha level be that would match? Yeah, it'd be 2.5%, right? Isn't there 2.5% in the tails in that guy? So we wanted, if they match, this would be 0.025. All right, assumption 1. Anything changing? Simple random sample. And we're doing our same analysis, right? Assumption 2, anything changing? We're just trying to see if that's the right formula to use, right? So that stays the same. Assumption 3. Now I'm going to normal sampling distribution. I'm going to abbreviate. You're not allowed to. But that's what we're looking for here, right? Do we have a normal sampling distribution of all the p-hats? Here's our formula. So what do I plug in here? The sample size was 1,200. What do I write next? What do I put in there?
Your p-hat that you're selecting.
My p-hat's 51%, right?
No, your
Yes, that's what I put in there. Don't I have this now? I actually have this. In the confidence interval, I didn't have that value. But here, I know what this is, so that's what I'm going to use. Don't I say right off the bat, P is 0.5? So if I see P, 0.5. So that's different than the confidence interval. So this is going to be 0.5, 1,200, it's going to be 0.5 again. Those are actually both 600. I can do that math. Those are greater than or equal to 10. Yes, I do have a normal sampling distribution of p-hats here. Test statistic, remember it's a z-score now, no t-scores. So the z-score formula is, okay, I got 51%. You say it's supposed to be 50, and that's what a standard deviation is. That's the standard error of the proportions. So formula you used way back in chapter 9 when we were learning about this stuff. All right, let's draw our picture. These are all the possible p-hats. What's going to go right here? Go, Jason, you got it. What? That's 0.5, right? That's what we're assuming to be true. We went and took our sample of our 1200 and we got a p-hat of 51. 51% is what we think, based on our sample, he's going to get. That's the p-value for this problem. Go plug in your numbers. Wow, we got 51%. You say it's supposed to be 50%. I got a percent more. Is that enough? All right, now what goes down here? What numbers are we plugging in down here? 0.5, right? We're supposed to plug in the population proportion here. We didn't have that value over there, but we have it here. 0.5 times 0.5 over 1200. Throw that in your calculator. Make sure we all get the right z-score. Get one yet? Around 0.69. I still have some of you losing points on your test because you don't bother to put it on your picture. That needs to stop. All right, go to your z-charts. You've been looking at t-charts now for a while. Do you remember your old z-chart? Take a look at that guide and make sure you can find that p-value. What do we got?
0.757.
Ooh. 0.24. All right, we got subtracted, right? 0.2451. And what does this mean in English? Remember, you say the real mean's supposed to be. You say the real proportion is supposed to be 50%. Oh yeah, I got 51%. That's consistent. That's going to happen 24.5% of the time if 50% is the real answer. If on election day he's going to get 50% of the vote, me taking a sample and getting 51% is pretty likely. So I don't have proof he's going to get a majority of the vote. Conclusion, we got our same three-sentence conclusion. Assuming Obama's going to get 50% of the vote on election day, the chances of getting a sample proportion of 51% or more is 24%, 25%. Since our p-value is greater than our alpha level, we are not going to reject. Therefore, we do not have statistically significant evidence to say Obama's going to get a majority of the vote. Okay? So like I said, we got a test on this coming up in a few days. There's not that much to it. Now what am I going to be looking for? Do you understand the subtle differences between a hypothesis test and a confidence interval? Okay. And the whole big deal is right there. That's the big deal. Okay. Show you one more thing. Let's say we're just, starting out a problem. And before I go take my sample, I want to make sure I take a big enough sample size so that when I do my math at the end, I'm going to get a margin of error that I like. So, it's the same old margin of error kind of problem. This is our margin of error. So, I don't know, let's say we're doing a 95% confidence interval. I want my margin of error to be plus or minus 2%. How big of a sample do I need to take? Okay, so that's the problem that we're met with. So here's our margin of error formula. So the margin of error is equal to the Z crit times, and this is the formula. Let's plug in the stuff we know. This is totally different than the Obama thing. We're doing our own separate problem. We're trying to figure out the percentage of people who like daisies the most. It's me. You laughing at me? I like daisies. So I'm trying to figure out the proportion of people in the country that like daisies the most. James, you're with me, right? Daisies. Okay, so but I want to make sure that when I get my final answer, I've got a margin of error plus or minus 2%. All right, here we go. I want the margin of error to be 2%. I said a 95% confidence interval. Now you can read ahead and talk to me. Do I have any idea what the percentage of people in the world that or country that would pick daisies the best? Do I have any idea what that is? No, I don't. So here's the deal. If we don't have any idea, and I haven't taken a sample yet, right? It's not like I plug in p hats. I haven't even taken a sample yet, right? I'm trying to figure out how big of a sample I need to take. So here's the rule on this. If you have no idea what the population proportion is going to come out to be, use 0.5 for that value. And what that'll do is, so if we use 0.5 here, and then 1 minus 0.5 over n, it will make sure that n is as big as it needs to be. It's kind of like the worst case scenario. Let's say I do this formula, and it comes out and says, okay, you got to ask 400 people. Okay, I go out there, I find 400 people from the whole country, I take them out of a hat, I go find them all. And then at the end, what if I really needed to find 405 people? Well, I'm in trouble now. Okay, I messed up. So I want the worst case scenario right now. What will give you that is 0.5. Now, I think you do a problem tonight or tomorrow, and they'll tell you what the population proportion probably is. If that's the case, go ahead and plug in what they tell you. But if you have no idea what that is, go from here. All right, let's do some math. Work backwards, see if you can figure out what that n must be. You got a couple of decisions to make here, algebra-wise. I want to get the n by itself. And the n is under the square root, so be careful. This is where you need to show what's our first step? By? Okay, so let's get rid of that 1.96. I like that. Okay, so now I've got that equal to that. What do you want to do next?
Square.
I would square it, right? Get rid of that square root. So let's square both sides. All right, let's clean this up now. This is the part that usually gets people. Okay, this is the part that people mess up on. So here's what I've got now. I've got 0.02 over 1.96 squared is equal to 0.5 over n. What do you want to do now? Okay, multiply by the reciprocal. So multiply both sides by n over this?
Oh. No, you take the right side, multiply that by 1 over 0.5 times 0.5, and you take the left side and multiply that by the same thing. So that you have, but then you have to take
Then I got n on the bottom still, right? All right, there's different ways you can go here. And I don't know if this is the best or not. Isn't this just one number? I mean, I see it as a fraction, but if I put this in my calculator, would it just be one number? So one way to look at this, and then cross multiply. That's one way to look at it. No? Too many fractions?
No,
Huh? So, That's the way I like to do it. So I'm going to have on this side, I'm going to have n times 0.02, 1.96 squared. On the other side, I'm going to have 0.5 times 0.5. Last step is divide by this thing. I know. That's the big guy you put in there. So if you've got a nicer way at this step to do it, that's fine. There's lots of ways. You can bring this up here and this down here. That's basically what you're doing. You're just switching those two. Go ahead and calculate us to make sure we all can get the same number. Oh, no. What do you got? 24? Anybody got a 24? Did you round up? 2401. You'd have to take a sample size of 2,401 people. If you do, your 95% confidence interval will have a margin of error of plus or minus 2%.